What if there was a place in space where time itself seemed to stop and the very laws of physics fell apart? Welcome to the world of black holes, the most mysterious and powerful objects in the universe. But what exactly are they, and why do they fascinate scientists? Today we'll dive deep into the science behind black holes. At its simplest, a black hole is a region in space where gravity is so strong that nothing, not even light, can escape. This immense gravitational force comes from a massive amount of matter compressed into a very small area. The boundary of a black hole, known as the event horizon, is the point of no return. Anything that crosses this line is lost forever, unable to escape the black hole's pull. Black holes form when massive stars die. When a star runs out of nuclear fuel, it can no longer support itself against its own gravity, and it collapses. If the remaining core is large enough, it keeps collapsing until it forms a singularity, a point where gravity becomes infinite. This singularity is at the center of the black hole, hidden behind the event horizon. Black holes come in different sizes. The most common type, stellar black holes, are born from collapsing stars and typically have masses up to 20 times that of the Sun. Then there are supermassive black holes. These titans lie at the centers of galaxies and can have masses millions or even billions of times greater than the Sun. Interestingly, scientists are still unsure exactly how these supermassive black holes form. There's also the possibility of intermediate black holes, larger than stellar black holes, but smaller than supermassive ones. Although these are rare, they could be the missing link in understanding how black holes grow over time. So what would happen if you fell into a black hole? As you approach, the gravitational pull increases dramatically, causing an effect scientists call spaghettification. Your body would be stretched like spaghetti. To an observer watching you from a safe distance, it would look like time slowed down as you neared the event horizon. Once you crossed it, you'd vanish from their view. But from your perspective, time would continue as usual until you're drawn toward the singularity. Inside the event horizon, the laws of physics no longer function as we understand them. We don't know exactly what happens at the singularity, but it could be a place where all matter is crushed out of existence, or even a gateway to another part of the universe, though that's purely speculative. Interestingly, black holes don't just sit there sucking everything in. They only pull in matter that gets too close. In fact, if our sun were replaced by a black hole of the same mass, Earth and the other planets would continue to orbit it just as they do now, though the lack of sunlight would be problematic for life. In 1974, Stephen Hawking made a groundbreaking discovery. Black holes aren't entirely black. He proposed that black holes can emit what we now call Hawking radiation. This radiation allows black holes to slowly lose mass over time and eventually evaporate. Although this process is incredibly slow for most black holes, it challenges the idea that they are eternal. There's also the tantalizing possibility that black holes could be linked to wormholes, theoretical tunnels through space-time. While the idea of traveling through a black hole to another part of the universe sounds like something out of science fiction, it remains a purely hypothetical concept. If wormholes do exist, surviving the journey through one would likely be as dangerous as falling into a black hole itself. Black holes have captured the imagination of filmmakers and writers too. Movies like Interstellar have portrayed black holes as time machines or cosmic portals. While these depictions are dramatic, they're often inspired by real science. For instance, the black hole in Interstellar was based on actual models, with its swirling accretion disk closely matching what scientists believe would appear near a real black hole. But how do we study something that's invisible? We can't directly observe black holes because they don't emit light, but we can detect their effects on surrounding matter. For example, when a star orbits an unseen object with a massive gravitational pull, we can infer the presence of a black hole. Scientists have also detected gravitational waves, ripples in space-time caused by collisions between black holes. These waves were first observed in 2015, providing a new way to study these cosmic giants. Black holes challenge everything we know about the universe. They push the boundaries of our understanding of space, time, and gravity. As we continue to uncover their mysteries, black holes may one day reveal answers to some of the biggest questions about the universe itself. For now, they remain one of the greatest enigmas of the cosmos.